Hello. In this video, we want to look at the derivative of e to the x to begin with. So the derivative of e to the x is just e to the x. I'm not going to go through the proof of this. If you want to see the proof, let me know in class. Now, here's the thing. The reason that we love the natural log, or the natural exponential, the natural number e to the x power, is because the derivative of e to the x is e to the x. Now, technically, there is an extra factor here of multiplying by the natural log of e. But the natural log of e is just 1 because the natural log of e means log base e of e. And anytime the base and the argument are the same thing, you get 1. So technically, this is just e to the x times 1 here. But what if we have a to the x instead of e to the x? Well, a is any constant that is, greater than 0, not equal to 1. And so if we take the derivative of that with respect to x, it's going to give us that same a to the x, but with that natural log of a as that factor there. So this does exist up here. It's just the natural log of e is going to be 1. Okay. So basically, here's what it says. The derivative of an exponential function is the original function times the natural logarithm of the base. Awesome. Now, here's the thing. What if we have a to the g of x and e to the g of x? Well, first of all, let's look at e to the g of x. d by dx of e to the g of x, in other words, exponential to some function of x instead of just x itself, is again that same e to the g of x times the derivative of the exponent. Now, this is basically just the chain rule. That's all it is. So take the derivative of the entire thing, which is e to the whatever it is, times the derivative of wherever the x is. In this case, g of x. In other words, the derivative of the exponent. Now, if we have a to the g of x, the same thing happens, a to the g of x times g prime of x. So just rewrite it, times the derivative of the exponent, but you still have this factor of natural log of a there. So technically, it does exist down here again, but it's going to just be the natural log of e. Now, for the logistic function. Frequently, a population or the series or the cells of a certain product will start growing slowly, then grow more rapidly, and then gradually level off. Such growth can be approximated by a mathematical model known as the logistic function. And here it is. G of t equals m g naught all over g naught plus m minus g naught e to the negative kmt. Now, there's another way of writing this. We'll see that in a second, where t represents time in appropriate units. G naught is the initial number present. M is the maximum amount, the maximum possible size of the population. K is a positive constant, and g of t is the population at time t. It is sometimes simpler to divide the numerator and denominator by g naught, and you get the following. So you get g of t is equal to m all over 1 plus m over g naught minus 1 e to the negative kmt. Now, one thing to note with all this is that the limit as t goes to infinity of g of t is actually going to be m over 1 plus 0, which is just 1. Now, the reason it's 0 is because the derivative of e to the negative t, basically, is going to be 0 because the exponential drops off as t goes to infinity if it's a negative exponent. So it's going to look something like this. So it goes to 0 as t goes to infinity. Alrighty. Well, there you go. I believe that's it for this video. I'm going to go ahead and end it here, and we're going to start working with derivatives. I'll see you there.